When your friends ask you, what did you learn in this course? What do you answer them? In today's lecture, we're going to explore ways how you can give them a great answer, which would be, let me show you. Welcome back to another edition of the Applied Deep Learning course. Today, we're going to explore exactly that. We're trying to see how we can serve, optimize, and take into consideration other practical aspects of showing other people what we did. But before we do that, let me quickly recap from last week's lecture. Last week we talked about a couple of things. We started with data augmentation. So what is data augmentation? Well, it's a way of creating meaningful but fake data to enrich our set of data that we can actually train on. Sometimes it might be quite hard to gather a lot of data, and with data augmentation we can artificially stretch those samples that we actually have. And as a nice side effect, our network becomes more robust against those transformations that we introduced with data augmentation. What is regularization and why should it be used? Regularization are the strategies to reduce the test error and to make algorithms in general work better in real life at the cost, though, of increasing our training set error. So what we're doing is we're basically limiting the capacity of our network in such a way that we do not overfit our data. We're regularizing our network, we're reducing the capacity in one way or another to ensure that we generalize well to previously unseen data. What are the most common strategies for regularization? I showed you a couple of them. One would be early stopping, by which I mean we stop training once our validation metric does not improve anymore for a couple of epochs. Another one would be data augmentation or weight decay, batch normalization, dropout. So there are a lot of different strategies that you can apply in your network and see which ones of them work best. Some of them have certain drawbacks, but we've discussed this already last week. How can the effect of batch normalization be interpreted? Batch normalization was thought of as reducing this internal covariate shift of the distributions inside our network shifting constantly, but it turns out that a more probable explanation for the effect of batch normalization is that it smooths the gradient, and by smoothing out the gradient it's easier for us to walk downhill towards the valley of our gradient. One example where it particularly can help is when you think of your valley having deep dimples, then you might get stuck at those local minima. Whereas if the network sees a surface that is very flat, it will just kind of roll down that gradient to the lowest point. So in other words, we're trying to reduce the chances of getting stuck in a local minima with batch normalization. Let's talk about some of the practical aspects. So a machine learning workflow, or data science workflow if you will, in practice usually looks like this. First of all, we collect data. This is one of the most important aspects, and I can't stress this enough. You need lots of clean data. You have to maybe crawl some websites to obtain that data set. You have to collect and annotate that data. So there is a lot involved in here, and if you can't get this right, you will produce only garbage in the end. You know, garbage in, garbage out. Once we have data set that we want to train on that is annotated and verified, that it has a high quality, we can move on to the, I would say, kind of core of our machine learning workflow, which is to train a model. We went through great lengths in this course already to discuss exactly this part of the workflow. So how do I find a suitable model for my problem? How do I train it? What are the benefits of using one or another strategy? And ultimately, if you're doing training, you will always have to fine-tune some of the hyperparameters that are not learned, but that we have to specify to the training and kind of have to specify how a network operates. And the big question is, now we got this fantastic model. It has 95% accuracy and it's doing a great job at whatever we want it to do. But what do we do now? So there is a third step that often gets neglected, which is unfortunate because it is very important as well, which is serving the model. We're trying now to prepare our model and what we've achieved in our training to make it reusable, to prepare it for execution or in some other way to run inference on actual data that we have gathered, where we want to have this in operations. And sometimes we might also encounter the situation that we want to continue training our model. So we have an initial draft, which was trained, say, on 1,000 samples, and then we put it into production. We use this as a kind of bootstrapping method to get the process up and running. And then from that operational output that it produces, we kind of just filter out data that we use for a second, maybe a bigger training set that we use in the second iteration. So we train our network again, have new weights, and then therefore we want to update our models in production as well. So that is an option for many real-world systems where we have this continuous improvement, where we need versioning and many other stuff. So that's all included in serving a model. The simplest way how you could serve a model would be the following. You go ahead, you train your model on a machine that runs any particular toolset that you preferred to train your model on. It could be PyCharm on a Windows machine, whatever. So you train your network on that, on your problem, on a specific hardware and on a specific software version of your tools. Once you're done with the training, you save your model and you just publish that model. So that kind of dump of your model, the snapshot of all the weights and all other parameters that are relevant for your neural network are saved. For example, you can upload it to GitHub as a release, which is commonly done by many frameworks and by many people who are training these models, that they just upload their trained models to GitHub, therefore making it easy for other people to reuse them. So that's one way how you can do this. And now if someone comes across your project, what they would do in return is they take your trained model that was trained on a particular machine, and then they have to recreate that environment, kind of the same tool chain, or at least compatible tool chain and versions of the software that you've used. And then they can execute the model and properly run inference. The problem is that I've seen big pieces of software being developed over and over again because of one issue. People are not willing to invest time to get an existing tool up and running. So while all frameworks have the option of doing this simplest way of serving a model, we have this problem that, we have to recreate that environment. So it requires a significant amount of knowledge to know how to get that environment up and running and how to execute that model. We need to build and maintain our tool chain. Deep learning frameworks have the common phenomena that they see lots of updates, and many of those updates are incompatible. So whenever you have like a major update, it could very well happen that your tool or whatever you build does no longer work. It might even happen with minor updates of your framework. I've seen this a couple of times already with TensorFlow, that they're moving so fast that I was constantly upgrading my models and updating it to allow me to continue using that framework. So if you want your tool to be available and usable for a long time, you would be in a difficult position now, because you force people to use a specific version of the toolchain that you used, and you cannot guarantee that for future versions that they might be using right then, your model still works. So unless your project is very well documented and it's easy for everyone to be able to replicate the environment and run your model, people will not use it. So a better solution would be to serve the model in a way that it can be consumed more easily. Imagine that you're going to a restaurant. You're not being served a raw piece of meat, but instead it's being cooked, it's being prepared and decorated nicely so you can enjoy your meal in the restaurant. And ideally, we as developers should do the same thing for our work that we want to present and someone else to consume. So one example how we can do this is by packaging it in an executable form where people can just run it straight away without the need for setting it up. You can run your executable, or you can prepare an executable that runs in a web application, a mobile application, or even desktop application. All of those are still very popular, so feel free to pick whatever you deem most appropriate for your project for people to run. I can speak from experience that web applications are an excellent choice, because all people need is a web browser, and you can open that on a mobile device, you can open that on a desktop, and then allowing people to just use your software project in that browser. You can also package everything and put it in a self-contained container. We'll talk about this a bit more in a second. Or if you intend to provide your service to other programmers, consider using a REST API, which is a standard way of allowing other people to consume your services on the internet. One thing I want to point out is that if you manage to get your model packaged into an executable file or into something that people can execute easily, you will get one benefit. People can play around with it, they can experiment with it, and it's much easier to evaluate and understand what's going on here if I can just play around with it. That's actually one of the reasons why some of the Japanese restaurants are having plastic menus outside of the restaurant that show you what you will get once you enter that restaurant. It's not very popular to see it in Europe, but at least in Japan they're doing this. And I think it's a good first impression of what you can expect from something before I actually invest a lot of time into getting this up and running. So this is really helpful for you if you want to make it available to other people. One thing I have to say here is that all of this packaging and making it ready for deployment is not unique to deep learning. It should be applied to every software development project that you think about how to bring it into operations. And if you go into that direction, it's called DevOps, like the mixture between development and operations. And in my opinion, every developer should have at least some knowledge of how to get their application up and running into production. Serving models in a more practical aspect, you can use Tensoflow Serving, which is one tool how you can easily take any trained TensorFlow model and expose that model as an HTTP endpoint with a REST API. So you basically take your model, you train it, and once you have the trained model, the TensorFlow serving environment allows you to wrap that model into something that can be executed and even updated continuously. If you think back about what I said at the beginning, that we want to continue training and then have updates of our model, TensorFlow Serving allows you to do exactly that. Let's take a look at an example of how this TensorFlow Serving looks like. I'm in Google Colab now, and what you can see here is the demo application of TensorFlow that shows how to use TensorFlow Serving. What we're doing here is basically training MNIST, but instead of using the old-fashioned digits, we're now using the fashion MNIST dataset. That is, I think, a brilliant idea to replace those boring numbers with something more appealing or something more fun. So they have a dataset of 70,000 grayscale images that have the same dimensions. So you can replace the MNIST dataset with the fashion MNIST dataset wherever that is used. And they have like shoes and trousers, shirts, dresses, bags, all sorts of, like, I think all sorts of objects, but the same kind of dimensions. So 70,000 images, 10 categories, 20 by 28 pixel grayscale. So has the same dimensions. What we're doing here is we're loading the data set. We are training a very simplistic model here with just one convolutional layer and then a dense layer. And after 5 epochs, we stop this with, say, an accuracy of 87%, which is not fantastic, but it's good enough for our experiment here. Once we have this, once the training here is over, we have this model. We can say we can save that model into the standard format that can be consumed by TensorFlow Serving. And now let's see what TensorFlow Serving can do. So we can examine the saved model to just get a rough insight into what's going to be in there. So basically, what are the input and output dimensions? This can be really helpful to see how to use that model, because some models, you know, might have been trained on 10 classes, other models were trained on 20 classes, and if there's a mismatch, it will break down. So you can use this to inspect your model before you load it. Now, what's being done here is we're actually initializing the TensorFlow serving thing. Okay, now this is just a setting up for Google Colab to install the necessary modules. What happens here now is that we say TensorFlow model serve, which is an executable. We specify the port where it should be exposed, the model name, where the model snapshot can be found, and then we just run this on a background thread. So if you don't know this no-hub, it just means that we reroute our outputs to the server log and run this in the background. So what happens here is that we can now make our request to our model, and this is just to inspect one of the loaded examples. In this case, it's a t-shirt. And what happens now is that we put our samples into a data, into JSON dictionary here. And that contains our 3 samples from our test images. And now we can take that data and call our REST API by saying requests post with that data, and we're getting back the JSON response, so we're unpacking that. And now let's take a look at the result. In this case, it's a boot, and it actually is a boot. So the predicted class was boot, and it actually is a boot. We can also do this for more samples. So let's say, okay, please run this not for 3, but for 30 samples. So let's rerun this request. Now we just predicted 30 samples, and now we also have to change this here. And now we're gonna see lots of predictions, should be 30. So it was an ankle boot, and it's actually an ankle boot as well. Pullover, trousers, yeah. Looks pretty good to me, even though it was just trained for 5 epochs. The network was really able to pick up this quite fast. I actually don't see any errors here, so it was a really good training. Okay, let's head back to our lecture. We can also serve our models in the cloud, and we have kind of a spectrum of how we want to serve our models. One way would be so-called infrastructure as a service, IaaS. For example, just a virtual machine that you can rent. Basically, someone giving you the keys to their computer, and you can do whatever you want on that machine. You have root access. So that's definitely one option how you can do it. It's also quite intensive in terms of maintenance, because you have to maintain all the packages, software, distribution, updates, and so on and so forth on that server. So if you're willing to invest that kind of time and knowledge, you can definitely do it. On the other end of the spectrum, you can have platform as a service, basically having a service or a ready to execute tool that you rent. Azure Machine Learning Studio would be one example here. And it looks like this, where you basically click and drag together your pipeline that you want to execute. And then in the middle, there is your training step. And then you can say, okay, that's my model, please, and my entire pipeline, please run this thing now. 2 more examples about platforms that you can run machine learning algorithms as a service. One would be gradient.run. You can find it at gradient.run, which is a commercial platform, which is like this one-stop shop where you go, you can train your models, you can store them there, and you can deploy them. So this is also like an example of where you just have one platform and you pay for them to run the machines, to train, and to run the models afterwards. And one last example that I personally find to be a really nice example of such a platform would be Streamlit. It's not just a platform for running, but actually an open source framework for building web applications for serving machine learning and data science applications. It's available in Python, and it has this really nice framework that allows you to quite easily build an application with some nice graphical user interface that you can also host on their website. So they're offering this platform here as a service as well. And of course, they also have a commercial model available if you want to have more applications or more servers, more performance, more memory, etc. Then you would have to pay. But Streamlit is definitely one of the options that I would highly recommend for your assignment number 3 to give it a go and see maybe you want to build your application with Streamlit. In between those 2 extremes, there is also a kind of middle ground where we can run containers. And that is a very, very popular way. If you've never worked with Docker and containers before, I highly recommend this. You will come across these at one point during your developer's life. And the idea would here be to package all of the code and all of the dependencies that are needed to run your code into that Docker container. And then your Docker container can be put on different hardware. It fires up really quickly, and then you're able to execute your script and then throw that image away. They're fully self-contained environments, meaning that all of the requirements that are needed should be inside of that. And compared to virtual machines that we would have with infrastructure as a service, they are much more lightweight, they're much faster on starting because they do abstract the operating system that is underneath. So it's, I think, a good middle ground where you're in control of setting up this, but anyone can take it and run it on an arbitrary software that runs Docker. Creating a TensorFlow serving Docker container is also not that difficult. Let's take a look. The entire code for running a Docker container almost fits on one page here. What we are having here is a Docker file that configures our image that we're being using for Docker. So Docker creates, this Docker file creates an image that contains all the necessary information and software packages. So we're starting with an Ubuntu operating system, and then we're installing some packages here. We're copying over some data, and for running TensorFlow model from the Docker container, we have to expose at least one port so someone can access to this. And inside of our Docker container, what happens is that we say, okay, where is our model being stored? So we copy it into that container, and then we can basically just run TensorFlow model serve, the exact same thing that we've just seen before, but now exposing this only in an isolated environment. So if something goes wrong, only that Docker container is being affected and nothing else. So if that crashes, the Docker container just crashed, you can restart another container. Whenever you train a neural network, it can be very helpful for other people to be able to run them if you enable your model to be stored in an exchangeable, interoperable format. One format that is designed to give you exactly that is the ONNX, which stands for Open Neural Network Exchange, and it is a community project that tries to make AI tools and frameworks more interoperable with each other. What you do is you train your model in your favorite deep learning framework, and at the end you export your model into a common denominator, into a common format that is understood by many other tools. And then once you have your model exported in that common format, you can load it and run it on whatever runtime your user wants to run it on. For example, you can train your model with TensorFlow, then export it, and then say, but I want to run it on a mobile device, so I want maybe to use PyTorch Lite, and then that should load it. I have to warn you, it's not always 100% guaranteed that frameworks are compatible with each other, because some frameworks support certain operations that other frameworks do not understand. So this is always a thing that you have to remember once you go through this Open Network Exchange format here, that you might not catch every framework and you might not be compatible with everything, but at least it should be very easy for people to consume your models now if they're using a different framework. There are a bunch of supported frameworks here like Caffe, Chainer, CNTK, ImageNet, PyTorch, TensorFlow. So you can see that the number of tools you can use ONNX with grows continuously, and basically all the big names are here. How would this look in practice? If I've trained my model with TensorFlow and Keras, I can say, okay, here is my model that is stored when you save it as an H5 file. So you load that model, you call ONNX machine learning tools convert Keras, you provide that model, and then you save the model again with another utility function of that toolkit. And there you go. That's your ONNX model that anyone can use with an arbitrary runtime that they want to use it with. There are many partners and organizations that are actively supporting this ONNX project. Again, I think most of the major players you can find here. I think one of the most interesting things is that Google is quite prominently absent from this list. So again, they opted out of this approach to make neural networks more exchangeable, which I think is very unfortunate, because I think lots of people are using TensorFlow and it would be beneficial in both directions to have people come to TensorFlow and people training TensorFlow and then using it with other tools if they would join this effort. But let's see, maybe they will join it in the future. You can not only serve the outcome of your trained model, but also another really helpful thing is if you worked specifically on a project of bring your own data to serve your data set for other researchers. This is particularly helpful, and I benefited greatly from this when I did my dissertation, because another researcher spent a lot of effort into creating one data set, and I'm really thankful to him that he made his dataset public, and I was given the chance to train my models on it and develop some interesting approaches and explore this. When you publish your dataset, this is the guideline that I can give you. It's abbreviated with the 4 letters F, A, I, and R, FAIR. What it means is that your dataset should be findable. In more detail, it means that you should have something like a globally unique and ideally persistent identifier, how people can find your dataset if they want to use it. It might sound easy to say, well, I'm going to maintain my website for forever, but reality is websites go up and go down, URLs change. So having a persistent identifier that reliably leads you to your dataset is really helpful. And there are many approaches how you can do this with Zenodo or other ways, how you can create this digital object identifier that will stay up to date even in the future. You should also have lots of metadata and rich metadata so people can find your dataset and understand what it's all about easily. Accessibility in terms of datasets means that your dataset should be able to be retrieved from that identifier that you published, and at least your metadata should always remain accessible, even if for some reason your dataset will be no longer available in the future. Coming to interoperable, you should use formats that are kind of broadly applicable and widely used. If you use a standard JSON format to describe your samples, there is a good chance that people are easily understanding what's going on here and know how to load that. If you use an exotic format, it might be harder to use your data in other approaches. One example I can give you here as well is for object detection. There are basically a bunch of standard formats, this COCO format, for example, how people present data sets for object detection. And if you're able to shape your data to adhere to the same format specification in this COCO format, people can just take your data set and plug it into all of those projects that expect a COCO formatted data set. So make sure that you figure out what format is the standard format for your problem and try to align your data set to that so people can quickly reuse it. Which brings me to the last to the last point, which is reusability. Ideally, if you describe your metadata well, then people can and will reuse your datasets, which is really helpful. And I think it's also a great feedback for you if you publish something and you get lots of feedback in the future of people asking you stuff about it or want to use it, and maybe even file pull requests to fix some minor issues and extend it. Those are great ways how you can get some feedback. And I think whenever you're doing like these projects where you gather a large data set that is a lot of effort, it can really help others on the machine learning community if you're publishing your dataset. One final note for reusability, make sure that you also always apply an appropriate license to your data, because if you do not specify any license, your data is your property and it's protected. So people might be hesitant of using it. If you use a more liberal license like the MIT license or a Creative Commons license, people can more freely use your dataset. So make sure you check out the appropriate license that you want. If you only want people to use in a non-commercial way because you spend a lot of effort in developing this but freely use it for research purposes, there are also appropriate licenses for that, like the Creative Commons non-commercial license. Running deep learning in the browser is an exciting way how you can make people aware of your findings and have people play around. I would even say it's the preferred way how you should present your results if you want people to quickly be able to play around with it. One toolkit that supports this is ONNX.js. So if you went through the steps I told you before and exported your model in the ONNX format, with that toolkit, you can run your model in the browser. It's a JavaScript library and it's based on Node.js. If you're familiar with that, even better. And it allows you to efficiently run the trained model in the browser. Whether you have a CPU or GPU, it should support both. In this small example, we have a model that was trained on the MNIST handwritten digit set. And what you can do here is just draw a digit. So I'm gonna try to draw a digit and, well, the network says it's probably a 0. Let's see if that changes anything if I continue drawing. Oh yeah, now it looks more like a 5. Okay, let's start over again and I'm gonna try to, well, it already knows that I'm going to draw a 5. Let's try one last example. So that's a 7, and if I do this, yeah, it should become a 2, even though it's not the most beautiful tool. Now you might wonder, yeah, I see the point of putting this up and running, but I'm not really interested in drawing digits. I mean, what good is this thing for? I can show you one example of very much the same thing here being used in a tool that many of you are probably using or at least know about, which is Google Docs. What you can do in Google Docs is resembling that demo very closely. So if you want to insert a special character in your document, it can be really challenging to find that character in this gigantic set of symbols, and by scrolling through here, you never find the right symbol. So what you can do instead is you probably know how the shape looks like. So you can either search by keyword or just try to draw the symbol. Yeah, that's it. So it's the Greek capital letter omega. That's exactly what I wanted. Let's try another example here of, say, a sum sign. Yep. And interestingly, it also gives us things that look pretty similar to the neural network. So everything that looks kind of like an E is also included here. And even though it has pretty much the same underlying technology like that MNIST demo we saw before, it is super useful to use, and I highly recommend this if you want to insert special characters. The next example I'm going to show you is from the domain of music, and more specifically from the Magenta project. The Magenta project has dedicated itself to making great machine learning projects from the domain of audio and sound, and playing around with that in I think, fantastic ways. There were a bunch of researchers trying to investigate how Bach wrote his compositions. And if you remember that doodle that Google put up on one of the birthdays of Bach, where you could actually harmonize music in the browser on the landing page of Google, that was the result of one of the Magenta projects. So let's take a look at one of the Magenta projects. And there are way more that you can explore on that website. Let's take a look at one demo. Okay, we're now in the Magenta demo space, and what happens here is that we have a model that was trained to play the piano. Let's see if we can hear something. Doesn't sound too bad. We can even extend this model by adding some conditioning. What happens here is that we say, okay, I want to play in the key of F major. Let's make it even more extreme. Say, okay, I want to, oh no, not G. G, so F, A, and C. Those. And you can see that if you're familiar with music, here is an F, here's also an F, but one octave below, and that F is being played a lot because we conditioned on that. If we say, okay, let's do another preset, let's maybe do pentatonic. So we only want the pentatonic scale, only 5 tones. In this case, only the black keys. We condition our recurrent neural network to only produce outputs from that kind of allowed scale that we're having. One final demo that I'm giving here is PacMan, and you can play PacMan in the browser. And what happens here is that you can train your model. So as you can see here in the image, I'm using the web camera now to train the model. So I say, okay, let's see if this works. No, that wasn't ideal. Say like when see if I can manage to do this. So when I raise my left arm, it should go left. Let's give it a few examples. When I lift my right hand, it should go to the right. And if I do nothing, it should go down. And if I put the hand in front of my head, let's move up. Okay, let's train. Okay, so it's trained in the browser now to do this, and let's see if I can play PacMan with my fantastic gestures. So if I'm not doing anything, so left, up, and it actually works. I can play PacMan in the browser by just using my gestures here, and it has actually learned to recognize my gestures in this browser right as you saw here when I just captured those few images. I think it's a great demo here, so feel free to play around with this and see what's behind it, because all of the source code is available and that you can basically use here for playing PacMan and trying this out on your own. Coming to the training part you can visualize the training progress in the browser as well. There is one fantastic example here that shows how to visualize the training progress in the browser. Keep in mind there is already a very good tool for that, which is TensorFlow, the Tensor board from the TensorFlow community. But here is just another example how you can kind of do this in the browser. In this demo, we're using TensorFlow.js, and what happens is that we show this visor here, the right panel, and whenever let's create the surface and then load the data. Yep, so those are a few sample digits. And then what we're doing is we're training a model to work on this MNIST dataset. So we start our training of a fairly simple model, which I guess also has just a few convolutions. I'm not sure where it's being written. So what you saw here is that the loss went down, I guess the accuracy is this, yeah, went up, and we can start another training. Okay, so we can also wait and do it at the end, but let's see if we get some other charts. So most of these functions is if you write your information in the Tensor board format, you can get this from the Google Tensor board. Otherwise, you can find here a nice demo where you can basically run this model training and evaluation and see the training progress right in the browser. Let's explore these two things. Yeah, a nice way of evaluating your stuff, and then a confusion matrix to see which class was misclassified most often. There is one final demo that I'm gonna jump right into, which is the ConfNet.js MNIST demo. It's also a JavaScript library where you run training on an MNIST dataset. But what I find very interesting in this project is that you can play around with those hyperparameters and you can actually inspect some of what your network is actually training. So what this example here does is that it visualizes the activations from your various layers. And you can also see the gradient, so basically saying where it updated something in the image or where the highest values for that gradient are. And as we go further down, the highest number here will be the softmax, the output here, and those are the activations for particular classes. Yeah. Here are some examples. I think it's a nice way to also visualize those activations inside of individual layers to see which layers are learning something useful and which layers, well, might not contribute much to that particular sample. Coming from that example, there are many other frameworks and tools that you can use to run models in the browser as well. This is a short overview of them that are taken from one survey paper. I recommend taking a look at that survey paper if you're interested in this and trying to pick whatever framework you want to use. There are, of course, the very popular ones like TensorFlow.js, but feel free to go into more depths in that paper to find out which of those frameworks is suitable for you. While putting models into the web and running it from the web browser is one option, there is also another option which is very popular nowadays of running deep learning on your smartphone. There are some lightweight frameworks because obviously running training or running high performance models on your mobile device that has only limited computational capacity and especially restricted battery, you might find yourself in a hard time. What you should notice here is that those interpreters that are deployed here, they are highly optimized to work well on different hardware, because some smartphones nowadays already have some accelerators for being able to run certain computations more efficient. while others might not. So you have to run all of the computations on the CPU. The converter of these tools also takes care of converting your model into a very efficient and compact representation that you can easily apply or that you can easily distribute to your clients by adding these additional optimizations to be able to run your model even if you only have limited resources. The benefits that you gain if you deploy your model inside of an application that runs directly on your smartphone is that you do not have to maintain powerful servers. People won't upload samples to your server where you have to run inference and then send the results back. So it's just using the computational power of your users that they already have. So you can reduce your operational costs. You don't have any communication latency and your application can run standalone even if there is no network connection available. This completely opens up new use cases that you might not have thought of before. So there is a large benefit of trying to run models directly on the end user. And finally, and not unimportantly, when you have sensitive information, like people speaking into the phone to dictate stuff, you have to be aware of the privacy concerns of that whatever is being spoken, how to handle that. If that data never leaves the phone, you don't have to worry about some data leaks along the way of someone grabbing that sensitive information because it never leaves the phone of the user. So that would also be the final benefit that you would gain from this. Wrapping this up, there are some more practical aspects that I want to talk about. There are a bunch of distributed implementations because for most real life data sets nowadays, it is not sufficient to have one computer with one CPU or one GPU. That means you have large data sets, very large neural networks that need to be trained, and there is only one way how you can manage to train such large networks in a meaningful time by parallelizing it. And there are two ways how you can parallelize it, basically by saying you use data parallelism and each machine runs on different samples. So what you would do is, if you say you have 4 GPUs, you cut your data set into 4 parts. Each part is being sent or put on a different machine, and that machine or that GPU only sees that part of your data. But now, if they only see one part of the data, you have to make sure that the model updates accordingly. So there is a gradient update or gradient sync step involved that is taking care of whatever was trained on one machine gets reflected on all the other models as well. Or you can do model parallelism by having multiple machines work on a single data point but run different parts of the model. So you kind of cut the model in the middle. One part trains the first few layers and the rest trains a different part of your model. Unfortunately, stochastic gradient descent is a completely sequential algorithm. So all of these algorithms for distributed implementations need some way to overcome this limitation. There is something called asynchronous stochastic gradient descent, where you can distribute this more easily. You can have multiple machines that run in parallel with one of these synchronization mechanisms, or you can have a parameter server that is taking care of all those updates if you have multiple machines that are training independently. One of the most common bottlenecks that you might have encountered yourself when you were training your machine is the data loading. Data loading can be very tricky. If you do it wrong, it will cost you a lot of time. So the naive approach of loading data, where you just open a file, you read from it, and whenever that is being done, you train on it. Then you read the next file, you read the next chunk from the file, train on it, that will cause lots of still stands in your training. Because when you're loading, your model is sitting idle while you're training, the model is sitting while you're training, the pipeline is sitting idle. So you have these two things, that one is in charge of getting more data and the other one is in charge of training on that data. And if they are waiting for each other, this can be super slow. The obvious solution to that would be to do some prefetching and decouple those two processes, where one process loads data continuously. This is often done by so-called data loaders that many frameworks readily provide to you, where you can prefetch some data, and then while the training step S is training on your sample, the data loader is already fetching the next few examples, or at least the next sample. You can also parallelize the data extraction, which is especially relevant if you have a very large data set that you store on a remote location, like an Amazon S3 server. So reading from that remote storage instead of local storage becomes the bottleneck here. Like, you have to wait for a specific amount of time before you receive your first byte, and especially when you're now using remote storage, it can take orders of magnitude longer to read data from here. And when you read a single file, the bandwidth that you have available from reading from one of these services might not be utilized very efficiently. So you should split your data set and in parallel and interleaved read from these different sources. So you basically already read a whole bunch of files that you directly feed into the training to utilize all of the bandwidth that you have available and avoid these bottlenecks. There are a few more data loading tricks that I would recommend you to at least consider for your project. You can parallelize transformations the same way that we parallelized our data loading. So we can put the transformation process into our data loading kind of environment. And if we have 3 data loaders, each of those data loaders can load and transform the sample in parallel. You don't have to wait until you get one sample before you start the transformation. You can all do this in parallel. You can also vectorize your transformations in such a way that instead of transforming just one sample, you take a bunch of samples, put them in a batch, and then apply the same operation, for example a normalization, to all of them at the same time. That can also be implemented very efficiently with many of modern CPUs and GPUs, where you have one operation for many data, and then the framework can highly optimize this. If you have data that is very expensive to compute, consider caching your data, at least while you're training, in such a way that you don't have to compute all those expensive operations over and over again. And finally, use a binary format for storing your data if you are reading from hard disks that still have mechanical components, where they're kind of slow on reading and slow with random access. There is a format called TensorFlow Records, which is a prime example of such a binary format where you can efficiently store your data and load it into memory by kind of reading large chunks at once that can then easily be used for training. To boost the performance of your training, there are still a bunch of other tricks. One would be to lower the numerical precision of your floating point operations. Standard floating point operations are 32-bit, where we have a large range of magnitude and enough precision to represent large numbers with high precision. And basically every hardware supports 32-bit floating points. One of those bits is used for the sign, to say whether we have a positive or negative, 8 bits for the exponent, which says how big our numbers can get, and 23 bits for the mantissa, which says how precisely we can represent our float number. Turns out that that precision and those magnitudes are rarely needed for machine learning situations. So instead of using 32-bit floating point, we can actually just use 16-bit floating point. So we use 1 bit for the sine, 5 bits for the exponent, and 10 bits for the mantissa. Alternatively, 1, 8, and 7 respectively for b float 16. So there are different ways how you can split those available 16 bits for your case. And what happens now is that you reduce the memory by cutting it in half. So all of your tensors now only have half of the size, and then you can just put 2 tensors next to each other when on your hardware and do 2 operations at the same time. So you're speeding up your training significantly by reducing it to 16-bit because you're reducing the amount of data that needs to be transferred, and you can parallelize the operations that are being operated on those data if you do it in a good way. One warning that I should issue here is that if you reduce your precision, you might run into the risk of overflows or underflows, where you either get the value of 0, although it shouldn't be 0, like small numbers become exactly 0, and multiplying something with exactly 0 will lead to 0. So we are having lots of multiplications in our neural networks, in our training. This could be a risk, because then we would eradicate all of the results from that neuron, even though it still had a value, even though it might have been quite low. And also, of course, overflows are a bit of a danger. There is specific hardware that supports these lower precision numbers called tensor processing units that are developed by Google, where they have an application-specific integrated circuit, an ASIC processor, that is designed for this high volume of low precision computation. So it clocks at a much lower rate, but given that it only has a limited set of operations and is highly optimized for this parallel processing, it gives very good performance while not producing too much heat while training. This begs the question, if we can go from 32 to 16, or with TPU potentially even to just 8-bit for our gradient or for our tensors, can we reduce it even further? The answer is yes, we can. There is an approach which is called 1-bit stochastic gradient descent, where we're actually trying to reduce the size to just 1 bit. What happens is that when we're training large data sets on a single machine, that's rarely possible, so we have to parallelize our training. And as I said before, if you split your data set and you run this in parallel, you have to synchronize your gradient. So you can either improve this parallelism by increasing the mini-batch size, by training on more samples at the same time, or by reducing the amount of data that needs to be exchanged between those individual nodes that are training your model. And this 1-bit stochastic gradient descent is trying to do the second thing by quantizing the gradient of your model to just 1 bit. So it dramatically reduces the amount of data that needs to be exchanged, while of course sacrificing your accuracy, and that quantization error that you can compute between what you have as an update step and what you actually send, it must be carried over, or otherwise, of course, you will accumulate a lot of errors here. It was developed by Microsoft and is available in their CNTK framework, which unfortunately is discontinued. Like, the development is discontinued, but I think this is still a very interesting idea of doing gradient descent. When we started this lecture, we talked about gradient descent and different flavors of gradient descent. There is batch gradient descent, where we take our entire data set, compute the gradient, and then take one step. The drawback of doing this is that we have to compute the gradient for our entire data set before we take a step. So it's numerically stable, but very rigid. On the other extreme, we can just take one sample, run it through our network, pretend that it's the the truth for our gradient and take an update step. What will happen now if you just use stochastic gradient descent with one sample, that it will be much more noisy because we're using expectations. We're assuming this gradient is an expectation of where to go. So the middle ground between just having trained on one sample or the entire data set is using mini-batches. We've discussed this before. And having large mini-batch sizes can boost your performance because then you're processing a bigger chunk of data at the same time, using your memory that you have in your GPU wisely, and being able to also be more stable in terms of your expectations that you can get for your gradient. So having this is usually beneficial, but just be careful that you're not too big, because otherwise you might exhibit poor performance again, either by overloading the memory of your GPU or kind of having this rigid version of gradient descent, as in batch gradient descent. So what you can do is that you can basically adjust the learning rate as a function of the mini batch size, which is something that you should definitely do. And you might even use something called Warmup. There is a rule of thumb that you can remember. If you increase your mini batch size by k, you should apply the same factor for your learning rate. Warmup means that when you start your training, you're starting it with random initialized values for your parameters. Taking a step in any direction here might be suboptimal because those are just random values that are currently in there. So it might be beneficial to start the training slowly, speed up to your basic learning rate that you want to have, and then slowly cool down again and reduce the learning rate as you progress through training to kind of not over jump the final solution. There is this kind of schedule here where you kind of constantly learn up and then have something like a cosine cooldown. There is even some papers that suggest that you should have the learning rate play this as a circle up and down continuously through the training to kind of monitor your validation performance and then either increase or decrease your learning rate accordingly. Once we have trained our big neural network that works excellently, we want to deploy it. But now we have a model that has 200, 300, maybe even a gigabyte in size. How should I put that on a mobile device? It's simply not possible. Luckily, we're able to tackle this problem in a couple of meaningful ways. There is even this myth that the human brain only uses a certain percentage of its capacity. I'm not sure if that is true. I'm pretty sure it's not. But I know that for artificial neural networks, it is the case. So running deep neural networks can be very computationally expensive, memory expensive, and ultimately also expensive in terms of energy, which is one of the most limiting factors if you want to deploy your model on a smartphone. So we have this large models that are slow to train and are only slow when we're running because the computer has to compute so many steps in our process. So if we want to run this on a less powerful device, it becomes prohibitive, like smartphones. The question is, does the network have to be that large? And the answer is, if neurons are in our network that are not contributing to our output, we can just remove them. And that is what pruning is all about. Pruning a network can be one of the two options. We can either prune synapses, where we say we want to remove the connections between neurons, or we can remove the neurons themselves. And what is being described here is also inspired by biology. Our brain does exactly the same. Over time, it removes connections that were established in our brain and also rebuilds some neurons that form new connections here. So what we can do in our artificial neural networks is that we remove all the neurons and connections that do not contribute to the result. Obviously, if we reduce the size of our network and remove neurons, we will reduce the accuracy. That means whenever we prune our network, we might need some form of reparation to make sure it still is operational. So we kind of partially retrain our model, maybe for a few epochs. And if we prune a very large part of our network, we might even damage it beyond repair. So be careful whenever you're pruning your network to not overdo it. One big question that is still outstanding is, how do we prune our network? How can we remove neurons? How do I find out which neurons are contributing to our output and which ones are not? There are two ways how you can do it. One would be weight pruning. So you set individual weights of your neuron to 0. And how to do this is basically by ranking your weights by their magnitude. If a weight is close to 0 and you apply that multiplied whatever input it receives, it will not change the value much. So when you rank all your weights by their magnitude, you can just remove the weights that, basically the connections that have the lowest weights. Similarly, you can remove neurons that also contribute the least by summing over the magnitude of all different weights. And then ranking the neurons and removing those that have the least L2 norm of the weights. By just setting them to 0, you can disable that neuron without actually changing the architecture here. And one very interesting observation is that models sometimes can be pruned up to 90% without a significant loss of accuracy. That means we have a model that is very capable of training, but we're only using parts of it. So the model found already enough information to not need the entire capacity. And we're doing 90% of computations without actually needing them. So there is a really good motivation here as well to try and play around with pruning. The question is, if we can prune the network after we've trained it, can we straight jump to training a smaller network and avoid all of this overhead of training this large model? And again, the answer is yes. There is a lottery ticket hypothesis that goes the following. A randomly initialized dense neural network contains a subnetwork that is initialized in such a way that when trained in isolation, it can match the test accuracy of another network, of the original network, after training for at most the same number of iterations. That might be a bit long, so let's break it down. We have a neural network that performs well. It is sparse, so we don't have a dense connection here, and it works fine. So the lottery hypothesis is that if we have a dense neural network, some of those neurons that are inside here are initialized in such a way that they perform very well and basically allow us to train very efficiently. So if we can identify those neurons that were initialized so good that it allows that subnetwork to perform equally well as the original network, we found the so-called lottery ticket. And again, one final question remains: how do we get this lottery ticket? There is an iterative magnitude pruning algorithm that can be used to identify those so-called winning tickets, identifying those neurons that were initialized in such a way that training becomes very efficient, calling those neurons winner of the initialization lottery. How you would go on and do this is by randomly initializing the neural network and then training it for j iterations, arriving at some parameters, some trained parameters. Now you go ahead and you prune your network p% of your parameters and thereby creating a mask to say, okay, which neurons I want to keep and which ones I remove. All of the remaining parameters you reset now to their initial values, therefore creating the winning ticket. Because you remember which neurons remained from the pruning, so we only want to keep them. We reset it back to their initial value, and then we have one of those lottery tickets, because that subnetwork was kind of trained to arrive at a good state. So they were initialized very well. There are some alterations of this algorithm. For example, instead of pruning the network just once and then training that subnetwork, we can perform iterative pruning, which repeatedly trains, prunes, and then resets the network over n rounds, and always just pruning a certain part of the weights. And instead of just resetting all the weights to the initial weight, we can also just go back a few steps by using so-called rewind instead of reset. So we kind of take snapshots and we only go back a few steps for all the weights that are that should be rewound. Coming to the end of this lecture, let's try to sum up what we discussed today. Deep learning requires the same amount of DevOps as many other software engineering projects, and you should familiarize yourself with ways how you can deploy and serve your model in such a way that it can easily be consumed. And actually exercise 3 will be exactly that. The task would then be for you to take your model, find a way how you can deploy it so we can play around with it and you can show all your friends how you can what you learned in this lecture and what you achieved. The trained models can be served in various flavors. Most of you are familiar with these, like an exported model that you just put in an artifact storage on GitHub, but there are also more accessible things like having an API for developers with a REST API, a Docker container, or just an executable like a web app executable or a smartphone application that contains your trained model and that people can play around with. Taking care of your data loading can be very beneficial to avoid bottlenecks. Parallelization here is the keyword. So don't sit idle while your model trains, but instead do something useful by loading the next samples from the disk. And reducing floating point precision or increasing minibatch size and ultimately using Warmup can be means to increase the performance of your training further. So speeding them up and trying to make it faster and more energy efficient ultimately. And before delivering a model, you should always at least think about whether you really need the large model in its entirety or whether you can actually prune some of the weights that are in there. And if you can prune it while not sacrificing a lot of accuracy, it is highly advisable to do so, therefore reducing the computational costs on your clients. So there are techniques to find the suitable networks while still performing equally as the full model, while now running at a much lower cost. That's all for today's lecture. I'm looking forward to see how you are going to serve your models to me as part of the exercise 3. Have fun with the exercise, enjoy exploring this great field, stay healthy, and I'll see you all next week.